Alright, welcome to this week's video. Today we're going to be talking all about the lungs. So, as you draw the lungs. Okay, so I have bronchi, come off here, and then they eventually go off into the alveolus, which are kind of like these little ball-like structures, and there's millions of them inside the lung. And the lungs are inside this cavity, our body. Draw some ribs. Space here, it's called the pleura, pleural space. And here, it's all lubricated. A little bit of water. That's the pleural space. And what's interesting about the lungs, and very specific about the lungs, is we have different pressures associated with this, especially with the pleural space. We have a negative pressure. So it's typically around -4, it can get up to -7. And this pleural space, what it does is it makes this lung, it suctions to it, and it moves up and down, and with this water-based substance, it's lubricated. We also have the diaphragm. So the diaphragm, when it's relaxed, it is curved upwards. But when it contracts, it goes down and flattens. And this helps us to increase volume to be able to breathe in. So there are negative pressures. So this is associated with Boyle's law. Boyle's law states that as that pressure and volume are associated with each other. So as we increase our volume, such as this contracting, we will lower our pressure, allowing us to not have a pressure to fight against. So as we lower that pressure, we can drop this pleural space from -4 to -7. These also in the alveoli. The alveolus is very vital to our gas exchange. So in the alveolus, we have different pressures, 1, 0, 2, oh, sorry, and 1. So, this -1, this is what happens after, during inspiration. After inspiration, it is 0, and then during expiration, this is 1. So this all occurs because oxygen flows from high to low. Okay, and then when talking about this alveoli, we have these different things associated with it. This area is called a type 2 pneumocyte. This type 2 pneumocyte is very vital. What it does is it produces surfactant. Surfactant is kind of like a lubrication. In this, it's a water-based substance. And what it does is it lowers the surface tension. So surface tension is important in the lung because we have these water molecules, and as we know from chemistry, Water likes to bond together. So this surfactant will help remove that surface tension. If we have a lot of surface tension, what can happen is we can have a lot of rubbing between within the pleural space and the edge of the lung, the visceral pleura and the pleural space, and that can cause a pneumothorax or collapsed lung. That's any way that we get a pocket of air inside the lung. What that does is it reduces our volume. That goes down. We have a higher pressure within inside the lung, causing the lungs eventually to collapse. So we'll talk about that. Under another lung. I don't know why the one side always looks half a heart. There we go. It's like a kidney. Sorry guys, my drawing is not the best. So once we have that lower volume and higher pressure, we have a smaller lung, causing us to have a lot of big pocket of air, not allowing that lung to work properly. So another thing we got to talk about, another law associated with the alveoli is Laplace's way. Laplace's law. I don't know why I said that like that. Sorry. He essentially stated that pressure is affected by tension and the radius. So as the lung is bigger, there's less pressure. Another thing that affects it is the tension. If you have a higher surface tension, you'll have a higher pressure. So that's why this surfactant is very vital. It helps us keep the pressure down, allowing us to inspire when we need to. Next, what we have is an equation. This is the alveolar gas equation. So we have the pressure, the partial pressure of oxygen. We have the fraction of inspired oxygen, FiO2, and we have partial pressure of the atmosphere minus the partial pressure of the water minus the partial pressure of the carbon dioxide over R. And in this circumstance, R equals levels of carbon dioxide over levels of water. And this is the RER ratio. And so we can use this to calculate the proper level of oxygen which is necessary. So typically atmospheric pressure is 760. We have a negative 50 of partial pressure of water. Typically the normal fraction is 0.21. And partial pressure of carbon dioxide is 40. We typically have a resting membrane of 85. Now if we're to calculate this out, pull out my calculator really quick. we would get a normal level of 140 of oxygen. So we can use this to determine different levels of healthy levels within the body. And so we can look at it and see if somebody has one of these issues with their health. All right, next we're going to talk about hemoglobin. So hemoglobin has these 4 heme groups with iron in the middle of them. So hemoglobin can bind 4 oxygens or 4 carbon dioxide, and they kind of go vice versa. They'll exchange, and you'll kind of see how this works as we talk about it. So we're going to start off, we're going to talk about a normal cell. So this is any cell in the body we'll talk about. We'll just bring up your hand. The great hand. So one single cell in there. I need to make that bigger. There's a cell. Here's the capillary. So the capillary carries the oxygen to the cell. So we have hemoglobin. Hemoglobin has these 4 oxygens put on it. And what it'll do is it'll bind to that, to the muscle of the hand, and it will transport that oxygen. As for carbon dioxide, it will build up in the cell. And it will build up in the capillary. So as it builds up in the capillary, it flows to an area of low concentration, and it will kick off one of these oxygens. It'll come off, and so it won't bind at the same site, but it will bind close to it, and it'll still cause that change to happen, that shift. So as we're talking about carbon dioxide in the blood, just in general, so this is the formula. So this hydrogen is also important. It can also attach and kick off one of the oxygens. So it kind of do that same thing. So this happens all within the cell, within the red blood cells. And then there's this transporter that will take bicarbonate. I put 2 there. It'll take bicarbonate and allow it to be in the blood. So we'll talk about levels. Carbon dioxide, it exists 70% as HCO3, bicarbonate, 23% within the blood is free floating, capillary, and that leaves us with 23% is within the red blood cell. 7% is in the capillary. Mixed up for a second. And that is And then as oxygen, O2, we only have 2% that is in the capillary, 2% in the capillary, and 98% in the blood cell. Okay, so this graph, or this little chart, it's a little bit different. Talking about capillary exchange, in the alveoli. So there's the alveoli. We have the blood running up against it, and we'll still have that red blood cell here. Still have that exchanger. So this is the partial pressure, ACO2. It exists in 40. The pressure in the venous return is 45. So this flows from a high to a low back into the alveoli. There's a higher affinity for the returns with carbon dioxide. Dumps it off there. That dumps it into the alveoli. And oxygen then flows in here, into there, kicks off that carbon dioxide, and you have a higher breathing rate. There's now a graph that we can represent this. This is called the oxygen hemoglobin dissociation curve. We have the graph, we have the hemoglobin O2 levels, and then we have the partial pressure of oxygen. So this is what a normal curve will look like. Kind of come up and plateau. But what can affect it? Use the mnemonic cadet. And so this is for a right-sided curve. We have increased carbon dioxide, increased acid, as we already mentioned, hydrogen. We have the DPG. So DPG, what it is it is a, so we have two states, this hemoglobin. Hemoglobin right now, it would be in the T state. It can make a conformational shift and allow for the binding of oxygen, and that would be considered the R state. So what this DPG does is it allows for an increase of the T state, which means that it allows, like we're talking about right here, it allows more carbon dioxide to come in, kick off the oxygen, and replenish it to the cell. So it will in turn affect breathing rates. Other thing that affects it, exercise and increase in temperature. These will all cause this to shift to the right. So we'll start the same, I'll come up, and come right there. Shift to the left, a little bit different, very similar, as you can tell, decrease in CO2, decrease free-floating hydrogens, and cold temperatures. So just a reminder, T state is deoxygenated, and this is oxygenated. All right, that's all I have to talk about today.